between space and planetary surfaces 2, and the chairs are Josh and Josh. That'll keep things simple. And so yeah, it's as it has been 12 minutes, and at 12 minutes we'll give you a warning, and then that means you've got a couple minutes to wrap up, and the sooner you wrap up, the more time we'll have for questions, and as you continue talking, we'll continue badgering. So yeah, we'll just get started with Katherine Burgess, EELS measurement of iron oxidation state in space-weathered lunar soils.
So change the title a little bit. I am unfortunately not going to tell you anything about the natural materials. I've had some sample prep issues, but I'll be talking about the technique that we use in the electron microscope and some of the recent advances in the technology that make the returned samples that we have still in pristine conditions and saved for so long, and kind of the new things that we can do with those samples. So as Larry introduced really well this morning, a lot of what we know about space weathering and the samples is stuff that we've found out using transmission electron microscopy and being able to look at the really fine scale nanoparticles and iron and amorphous rims that create the characteristic darkening and reddening of the spectra from the moon and from the asteroids. And then this is very recent work from this year's LPSC that Michelle Thompson has started doing EELS measurements of these nanophase iron grains and seeing that some of them are oxidized. It seems to correlate with maturity. And so the work that I've been doing as part of the RISE survey group and the theme of maximizing science from return samples is to try to make sure that when we do these measurements, we're assigning the correct valence state to these spectroscopy measurements. And so to do that, we have a couple different possible standards that we've looked at. Some of these are basaltic, andesitic, and rhyolitic glasses buffered at different oxidation fugacities. And they've been well characterized using Zanes and Mossbauer and in the microprobe. And I've prepared these using just a microtome, so they're just chipped up into very thin samples and laid down on a carbon grid. And then I also have some natural olivine phthalites that have been variably oxidized and have also been studied, and there are publications on some of these. And so we're looking at these both because they're well characterized, and so we can relate our measurements to these other measurements. And also, we're looking at these grains on a very different scale than most measurements are able to access. And so we want to know how those kind of bulk measurements relate to the very fine scale, nanoscale features that we're able to measure. So we use an aberration-corrected scanning transmission electron microscope. This is the one at the Naval Research Lab. This has the cold fag gun at the bottom, down here, this next to Rhonda, that goes through a series of magnetic and electromagnetic lenses. The electron beam passes through the sample, and then several detectors after it passes through, one of which is the electron energy loss spectrometer, which we have 0.3 EV resolution. We can run this at a variety of energy conditions. We have sub-angstrom spatial resolution and X-ray EDS detection down to the single atom in special cases. For EELS specifically, this is an inelastic interaction between the electrons in the beam and in the sample. And so the prism spreads the beam out according to the energy after it's passed through the sample, and we get a nice spectrum here. Because of the scanning part of this microscope, we're able to collect these as data cubes where each pixel has an associated spectrum. And for the iron L edge that we look at specifically, it falls around 708, but shifts due to chemistry of the sample and the oxidation state. And we're able to, both through some first principles, but mostly through use of standards, relate that directly to the oxidation state. In general, for this first peak, it's shifted to slightly lower energies for reduced and slightly higher energies for oxidized samples. The quantification of the iron oxidation state has several different ways to go about it. First step is to remove the background. It's relatively straightforward. And then we need to fit these peaks. One way to do this is to fit this first lower energy edge with a series of peaks, one that represents the more reduced part of the spectrum and one that's more oxidized, and then you can ratio those in various methods. Another way, and many of the recent publications use something along this, is to use a ratio of a window method where you take a window here and a window here, some under the curve, and fit it to this universal curve that's been measured with a variety of different silicates and oxide samples, and assign an Fe3 plus over total iron. This shows that the ratio of these is not linear with iron oxidation state. Sometimes it's closer to linear for this method, but it's unclear then how much things like structure and whether the iron is tetrahedrally or octahedrally coordinated does affect how well these methods work for the quantification. So I've started these measurements in a variety of olivines. These are natural samples from several different locations that are variably oxidized. And they're complex samples, and so every sample shows a large range of spectra and spectral features with a variety of possible oxidation states. Just qualitatively, it's pretty clear that this is all from a single sample, and the ratio of these two peaks varies quite a bit from kind of pure olivine where everything is Fe2 plus to something very different. And so for this plot, and most of the ones I've done, I take the ratio of this middle peak to the sum of these three peaks, which is why it never gets to 0 or to 1. But as expected, most of the San Carlos peaks are very reduced, although there are some areas that are relatively oxidized. And then the values from published literature data do fall kind of in the middle of the range of the spectra that I have, but I do see quite a variety. One of the ways that we'll be able to kind of get back to possibly either what the most oxidized part is, or to kind of filter through that data, is to look at the composition of these samples. And so these are selected EDS maps. This is iron, sorry that got cut off, manganese and magnesium, scale bar 200 nanometers. So these are just over 200 nanometers across, and you can see there's quite a bit of variation in the manganese and a magnesium-rich grain here in these phthalites. And then when you look at the EELS spectra associated with these different regions, so these regions here are 1 and 2, and so they have quite a bit of manganese in them, and then are very Fe2 plus rich, basically no Fe3 plus in those regions. And then this magnesium rich region, which from a map created from ratioing these two peaks, is not quite as reduced as the manganese regions, but it's lower in iron, so it fades out a little bit in this picture. And then region 4, that is very oxidized compared to that. And so it's easy to see that there's just a huge range of heterogeneity in these samples that we can pick out and measure and hopefully filter through to be able to relate the correct spectra to bulk measurements and try to get some kind of average in how they relate. The experimental glasses that I have looked at, I've focused on the basalt because they're highest in iron, although in an atomic sense, they're still not a lot of iron, and so these become very noisy spectra. But perhaps, I don't know if this is all that unexpected or not, on the scale of a few hundred nanometers, these are actually pretty heterogeneous, in oxidation state at least. They're highly susceptible to damage in the electron beam, any kind of the beam dwelling on them for any kind of period of time at all, has very distinct changes to both the composition and the oxidation state. But even filtering without that, there's significant heterogeneity. And so here I have the different oxidation states and the relative oxidation. And so the air ones are relatively tightly grouped and all quite oxidized. And at iron woostite and QFM, there are quite a few reduced samples, but also a number of oxidized samples. And so to look at the changes that may have occurred in the beam, I did separate these by dose rate and dose. And then this is actually relative reduction, and so now the high ones here are the most reduced. They're these samples. And you can see that at high dose rates, so high currents of the electron beam, and at high doses, we don't get those reduced samples. And so I have oxidized the samples. But at the lowest dose rates and doses, I see both the reduced samples and oxidized samples. And so within the same sample, at the same doses and dose rates, I see this variability. Some of this heterogeneity we're able to see when we map out just within very small regions of this glass. This is the Haddeth image of the glass, and if you look closely, there are lattice fringes in this, that it's at least nanocrystalline, and that these two regions have very different spectra. This one is quite a bit more reduced relative to this. In other regions, I find very small grains. These happen to be magnetite. There are very fine lattice fringes around here, but we can map out and pick out even these subtle differences in the sample, which these were not seen in Mossbauer of these samples, and so, but we do pick them up with the EELS. The damage that I was mentioning is really interesting. When the beam dwells for any period of time at all, we develop these spots. And when we look closely at the EDS maps of the ions, we realize that the silicon is relatively increased in these regions, but all other ions, and then the oxygen stays, but everything else has diffused away from this area. And then just to bring this back to trying to use these as standards and quantify exactly what the oxidation state is, that although in one sense it's very clear qualitatively that we're able to separate these oxidation states. Comparing the two methods, I showed the window method and these Gaussian fits. There is, a relationship that the oxidized ones are oxidized in both samples, but there's quite a bit of scatter, and so we need to deal with working through both reducing a lot of this error in these and then figuring out how to filter through and get rid of this scatter and relate these reliably to each other and quantitatively to the samples. So just to wrap up, we see this within sample variation in oxidation state at a very fine scale, submicron within these samples, which will make it difficult to relate the bulk oxidation values to our measurements, but I don't think it's impossible. These samples are susceptible to beam damage, but we've found conditions at which we don't see that damage. And then we will be doing fib preparations of the samples, both these glass ones in order to have large areas to look at and kind of get average oxidation states. And then we will be looking at the natural samples. We have some lunar basalts with this large range in maturity, and we have some high Busa samples we'll be looking at too.